and complex numbers. This is a very short unit in Algebra 2, but it's an important one. You're going to learn about the imaginary unit and complex numbers, simplifying powers of I, simplifying radicals containing negative numbers, adding, subtracting, and multiplying complex numbers, and you'll be able to simplify fractions containing a complex number in the denominator using the conjugate. You'll be able to describe how pure imaginary, real, and complex numbers are related. You'll be able to graph a complex number. And you will be able to find the absolute value of a complex number. Let's get started. In this first installment of video or audio, we're just going to look at what a complex number is in the imaginary unit. The reason for the name imaginary is that when these numbers were first proposed, people could not imagine such a number or really a use for them. The term imaginary was coined by René Descartes in the 17th century. It was actually a derogatory reference, since obviously such numbers did not exist and had no use. Today, however, we find the imaginary unit very useful in both mathematics and science. Electrical engineers in particular use the imaginary unit, which in some electrical engineering books you'll see represented as the letter J instead of I when you study electricity. Now, where do they fit into our number scheme? Well, all numbers fall under the big umbrella called complex. Pure imaginary numbers can be sitting out here, while a complex number is a combination of a real and an imaginary. Within the realm of real numbers, we have natural numbers, 1, 2, 3, 4, whole numbers, 0, 1, 2, 3, 4, integers, ... -3, -2, -1, 0, 1, 2, 3, 4, ... Rational, anything that can be written as a ratio of two integers, namely fractions. Decimal numbers that repeat or end. Irrational, numbers that do not repeat nor end. Now, you can treat a complex number just like a real number when adding, subtracting, multiplying, and dividing. You must simply remember that the imaginary unit cannot remain in the denominator. That's because the imaginary unit is the square root of -1, and we've already determined that we remove all radicals from the denominator. Now, imaginary numbers occur when a quadratic equation has no roots. Notice this is a quadratic, not a fourth, not a sixth, not an eighth, only something squared. So if we have x squared plus 1 is equal to 0, x squared is equal to -1, we take the square root and we get plus or minus the square root of -1. The square root of -1 is the imaginary unit. So right here, the square root of -1 is our imaginary unit, which we call I. Negative the square root is -I. That's all I is. I is the square root of -1. Now, when we want to simplify things, radicals that have negatives, remember that we can separate things underneath the radical. Also remember that 2i, -5i, 3i root 3, 3/2 I, these are all pure imaginary numbers. No real part to them, therefore they're not complex. If we take a look at this guy, this is the same thing as the square root of the square root of 4, square root of -1. The square root of 4 is 2, the square root of -1 is I. So we get 2i. Square root of -64. The square root of 64, the square root of -1. Thus, 8i. Now, I'm not putting plus or minus in front because the radical is already there. Now, here's an interesting one. Square root of -20. Square root of 4, square root of -1, square root of 5. Perfect square, imaginary unit, what has to stay underneath? The square root of 4 is 2, the square root of -1 is I, and the square root of 5 stays under the radical. We write it in this way so the I is not confused with its location. nor is the 2. It's 2i root 5. In a case like the square root of -3, square root of -1, square root of 3. I can't do anything about the 3, but I can take out the I. Now, pause the video and try simplifying these 4. Let's see how you did. 5i root 2, -6i, 2i root 6, 4i root 3. Just so you know, we've got the square root of 25, the square root of -1, the square root of 2, negative the square root of 36, square root of -1. We start with the perfect square, then the imaginary unit, then anything else that's left over. Square root of 4, square root of -1, square root of 6. Square root of 16, square root of -1, square root of 3. 3 times 16 is 48, negative 48. Again, these are all pure imaginary numbers. Now, how do we simplify something? Well, we have successive powers of I that actually produce a pattern. I to the first is just I. I squared, well, think about this. If I have the square root of -1 times the square root of -1, that gives me -1. Therefore, I squared is -1. Now, if I come along and I say, well, I have I cubed, that's the square root of -1, square root of -1, square root of -1. Root 1 root -1 is -1, and this last one leaves me with an I, therefore I have -I. I to the fourth, square root of -1, square root of -1, square root of -1, square root of -1. This gives me -1, this gives me -1, together it's 1. That's where I get this 1 from. Now, the pattern repeats. As soon as I have I to the 4th, it's I to the 4th times I, or just I. Because remember, I to the 4th is 1. I to the 5th is -1. I to the 6th is I to the 8th is 1 again. To help you remember the pattern, you can think, I won, and negatives in the middle. You have I, you have 1. You have I, you have 1. And you have the negatives in the middle. So again, it's I won, and negatives in the middle. It just helps to remember the pattern for the first 4, and then the pattern repeats everything after that. So let's take a look at simplifying some of these. If I have I to the 15th, I can think about that as I to the 4th. How many I to the 4ths? Well, that's 3. I to the 4th cubed is I to the 12th. How many are left over? I cubed. What is I cubed? -I. So here I have I to the 4th cubed. I cubed is equal to I cubed. What I want to do in all of these, I want to do I to the 4th some number of times. And then I'm going to have an I. I'll put an X over here. This is, whoops, let's try that again. This right here, what is it doing? I'll go like this. This is just 1. I to the 4th is 1. 1 to any power is 1. So then I'm just left with the remainder. So again, I to the 21, well, that's I to the 4th to the 5th times I. 4 times 5 is 20. It leaves me with 1 left over. So it's I. Try I to the 48th, I to the 30th, I to the 101, I to the 27th, and 12 times I to the 48th. See if you can get the right answers. Pause the video. Seriously pause it and try these. Great. Let's see how you did. Okay, we'll just move this off. See if I can't get all of these off. I don't know why this one doesn't want to leave, but we'll... Okay, there we go. How did you do? Hope you got them all right. Let's keep going. Maybe. Maybe it'll go, maybe it won't go. Okay, I'm going to pause and see what's going on. Hang on. Okay, now, back to the next slide here. You're going to need to remember that I is equal to the square root of -1 and I squared is equal to -1. Think about what happens when I is raised to a given power. I squared is -1. What you have to be extremely careful of when you're underneath the radical, the square root of -1 times the square root of -1, you cannot multiply negative numbers under the radical. You have to take out i's first. So the square root of -1 is I. The square root of -1 is I. That gives us I squared, which is equal to -1. Do not do this. You will have a wrong answer. Again, you must take i's out first. You cannot multiply negatives under radicals. All right, here are some problems. Whenever there's a negative under the radical sign, okay, it comes out from underneath as I, since the problem will contain the square root of -1. When simplifying radical numbers in terms of I, follow the usual rules for simplifying them and treat I with the rules as if you were working with variables. So here are some problems. And here's an example up here. Oops, there we go. Try these. Pause the video and try them. Okay, here's your solutions. See how you did. Again, you might want to pause the video so that you can take a look and make sure that you understand the work, the process to go from the problem to the solution. BI form is simply saying that this is a pure imaginary. We will be looking at some complex numbers in a few minutes. Okay, at this point I'm going to stop and we're going to come back and do a separate one for adding, subtracting, multiplying, etc.